Welcome to episode 14 of Q for Problems. Today's problem is problem 14 from the Project Euler problem set. This problem gives us a definition of the Collatz sequence. So that sequence essentially starts at some integer, and although it has not been proven yet, following the sequence you'll always get back to number 1. So the sequence is, if n is even, then you do n divided by 2, and if n is odd, you do 3 times n plus 1, and that sequence keeps going until it returns to 1. And you can see here in the problem it gives us the example starting at 13 and how the sequence evolves. So it wants us to find, starting with all the numbers under 1 million, which sequence actually produces the longest chain. So let's have a look at some solutions. So to start, we'll define a function called Collatz next. This function will have a simple job of getting the next term in the sequence. So by the definition given in the problem, we can create an if-else statement. So the first check is going to be if x, the input, is less than 2. We simply want to return x, so that would return 1 if 1 was input. Otherwise, we want to do x mod 2. This will check if x is evenly divisible by 2. If it is, then this will return 0, in which case it will actually do the second part of this if-else statement. However, if it's an odd number, this check will actually return 1, in which case that's interpreted as true, so it will do this first item. So that will be 1 plus 3 times x. And then if it's even, we want to just do x div 2. So this function is quite simple and just gives us the next term. So if I define that and then run Collatz next on 10, you can see that gives us 5. So if we go to 13, remember the example showed 13 and the next term was 40. So we run that and you can see it gives us 40. And if we actually want to follow that sequence through, we would then have to do Collatz next on 40, and from that gives us 20, which was the next term, and then we would have to do it on 20, etc. Of course, you'll probably recognize that this is a good opportunity for the scan or over. In this case, we want to use scan because we want to actually be able to count the total number of terms in each of the sequences. So let's create a function just called Collatz, which is going to actually do the full sequence, and it essentially just is Collatz next with a scan. So if I define that, and then I actually run Collatz on 13, you can see that gives us the sequence that we wanted before, that we had in the actual problem. So now we have to actually do all the sequences up until numbers under 1 million. So to actually do that, we will say, let's just do up to 10 to start with. So let's just go to the numbers 1 to 10. It will do the Collatz sequence for each of those. And to actually then get the list of those numbers, we just do 1 plus till, and that gives us all our numbers 1 till 10. From there, we do our Collatz on each of these numbers. So you can see that gives us all the Collatz sequences for starting at each of those points. You can see that when you start at 1, it just returns 1, which is correct. And you can see here is our 10, here's 9. You can see that they all start at different ones. So you can see here that 9 just visually is the longest, but we need to extract that information programmatically. So if I do count on this Collatz function, and that's going to actually now, whenever I do apply each, that's actually going to apply the count on each of these returns. So instead of getting these lists, you're actually going to get how long each of these lists is. So if I run that, you can see here that this one, remember, corresponded to this row here, which had 20 items. And then we actually just want to return the max of this. So I'll say r find max and then r assign. So r is this list of counts, and then you find the max r, which is going to be 20 in this list, and then you actually go through that list then again and find 20, and that returns us the actual position. So this is an index at the minute, so we would need to actually add 1 onto this number to return the actual result. So we can actually just wrap this now in our S1 and put brackets around it, just to define our S1 function. And then if we run S1 on 10, you can see that gives us 9. If we do 100, it gives us 97, 1,871. So these are the numbers that actually would produce the longest sequence under or within this number. So if I actually run it then for 999, 999, and we can see that that is the solution. So the previous solution was quite simple. However, it does take about 1 minute to run for the actual problem input of 999,999. So we can actually improve on this by, instead of doing this sequentially through all the items, we can actually do a vectorized solution, which will do it for all the elements at once. So we'll follow the same kind of naming convention, only we'll put a V in front for vectorized. So this is V Collatz next, and this is going to do exactly the same thing as the Collatz next, L, in that it will just get the next term in the Collatz sequence for a list of numbers input. To do this, we'll use our vector conditional. So the first argument to the vector conditional is a Boolean list of true and false values that essentially choose out of the next two arguments which value to use. So we'll do x equals 1. So anywhere that we have a 1, we're finished, and we'll just return 1 in that position. However, if we're not finished, then we need to then do a second check to check the even or oddness. So I'll just fill this out and then come back and explain. So it will be 0 equals x mod 2. So that means it's even, in which case we want to do x div 2. Otherwise, if it's false, we need to do 1 plus 3 times x. So to explain vector conditionals, I'm just going to give a small example. So let's say our test, it gives us 1 or 1001, and we then, on that test, we will choose values from the following. So 5, 6, 7, 8. So in index 0 of the test, we have a true value. So we need to go to the true part, and we need to go to the same index as this 1 was, which is 0 index. So we choose the value 1. Second value of our test is false, in which case we go to the false part. And then because this is in index 1, we need to go to index 1 here, which is 6. The third is also false. So we go to a false part and then go to that index, which is 7. And then the last is true, in which case we go to the true part and we go to the last, which is 4. So if I run that, you can see that that gives exactly the same thing. So that's exactly what it's doing. And just to note that even though in this example it's quite simple, so we don't have to worry about it, but it will actually have to execute both of these before it actually then starts replacing values. So that means that when we run this part up here, it actually has to execute this for all values of x. Even though some of the values of x are going to be 1 and they're going to simply return 1, this part will still be executed for those. But that's okay because it's quite simple in this case, but that is just something to note when using vector conditionals. So if I define that, and let's copy the name and run it on 1, 2, 3, 4, 5, and run that, you can see that this gives us the next term for 1, 2, 3, 4, and 5. So it's actually giving us the next term for each of these sequences starting at these values. And then if we were to run that, say, again for these ones, we could get the next term in each of those sequences, and so on. So again, we can just replace this by saying our v Collatz is equal to, or is assigned to, v Collatz next, and our scan, just as we did in solution 1. So run that, and then we can do v Collatz on 1, 2, 3, 4, and 5. Run that, and you can see this gives us the full list of sequences. So you can see that whenever it's finished, it goes to 1, and it just stays at 1 then until we actually get all the lists being finished, because the scan is actually going to be doing a converge. Basically, whenever it runs this and gets the same result twice, it will stop. So whenever you get to here, it's going to run again and then see that it's going to give us 5 ones again, in which case it knows that it's converged and we can move on. So to actually then do this for all the numbers up until 999,999, we'll just say x, our input is 10 just for visualization purposes. and we can do 1 plus till x just as before to get our list of numbers. And then we can actually apply our Collatz to this and gives us all those sequences. Now we can see which one's the longest by analysing the second last row. So you can see here that we know that this part was the longest because it's the only value that still isn't 1, because we know by the last row that everything would be 1. So the second last row is always going to be the row where we have the last value that wasn't 1. And of course, there could be multiple values that aren't 1 in here, in which case those lists are the same length. However, the problem just asks us to return the longest one, in which case we would just select the very first longest. So if there was a 2 here as well and a 2 here, then we would just select this one because we're going to use a find, and that will just take the very first value. So we just do a -2 take, and that gets us the very last 2 rows. And then we actually only want the last row, or the second last row, so we can just do a first of that. So you can see that that's give us the second last row. And then we just check where it's not equal to 1. So you can see here that this identifies this part as the only value that wasn't equal to 1. And then we just need to find the true values. So we can just use a find again. And I'm just using a projection form of this, just so rather than putting this whole thing inside here, it's just so it's executing on everything to the right. And you can see that that returns us the index. And again, we just need to add our 1 because that was the index and to get the actual value. And that agrees with what we had before. So just replacing now all this with S2. So we define that, and S2 on 1, 2, 3, 1, 2, 3, we get the same result.